now here today we will discussing about matrix formulation of the DFT and IDFT. If we let know the twiddle factor, the twiddle factor is Wn. Wn is equal to e power j 2 pi n. They define the defining relationships for the DFT and IDFT may be written as x of t is equal to the summation n is equal to 0 to where n is equal to 0 to n minus 1 x of n, the twiddle factor Wn k equal to 0, 1, 2, 3 and so on n minus 1. The inverse of this x of n, where it is this case x of n, where x of n is equal to 1 by n, the summation k equal to 0 to n minus 1, x of k into the twiddle factor Wn n minus k. Here it is the n is equal to, here it is k ready to substitute k equal to 0, 1, 2, 3 and so on. If the n is equal to 0, 1, 2, 3, 1, 2 n minus 1. So the first set of the n capital N DFT discrete Fourier transform equations in n unknown may be expressed in matrix form as x is equal to x, matrix form x is equal to Wn x, where x and x are the n plus n matrices and Wn is the n into n square matrix or the DFT matrix. The full matrix form of the described. So in terms of this, where x of 0, okay, the x of 0, x of 1, x of 2, x of 3, x of 4 up to x of what do you call x of n minus 1. Okay, so just we know this all are that waiting for twiddle factor Wn0 and so on. Here this value, you know that all how it is represented twiddle factor and multiplied with this what you call a given sequence x of 0, x of 1, x of 2, x of 3, x of 4 up to x of n minus 1. Okay, now we write to verifying this finding that the DFT of the sequence. The sequence is given x of n is equal to 1, 2, 3, 1, 2, 1, 0. So how we are evaluating this and the solution, discrete Fourier transform. Because of this mentioned the module what do you call 2 first fourth example, there is the meaning of 2.4. The DFT x of k of the given sequence is x of, this is the given data, x of n is equal to 1, 2, 1, 0 may be obtained by solving the matrix product as follows. Here based on this we can decide the factor n is equal to 4, when n is equal to 4. So according to this formulas, this twiddle factor, so here it is value is ready to, this value we know, this value, so minus j plus j plus j minus j minus 1 plus 1 minus 1 here. After simplifying this all are, so ready to verify here. After that we can use that x of 0, x of 1, here it is x of 0, x of 1, x of 2, x of 3, 0, 1, 2, 3. So after multiplying this matrix, we will expect this all as this 4, what you call 4 minus j2, 0 plus j2. Okay. Now after that we can decide the finalized result. The result is a discrete Fourier transform of x of n is equal to x of k is equal to what do you call that 4 minus j2 and third value is 0 and j2. Like this we are going to verify this all are finding that DFT of the sequence x of n is 1, 2, 1, 0. Next, find the DFT discrete Fourier transform of x of n is equal to 1, minus 1, 2, minus 2. Here, this case, see under solution, the DFT discrete Fourier transform x of k of the given sequence is x of n, where x of n is given 1, minus 1, 2, minus 2. Okay, so can be determined using the matrix as shown below. Same procedure here. We know that the matrix as like this, where x of k, a discrete Fourier transform x of k, we have tried that this matrix form. Okay, so based on this Tittle factor, weighting functions are like this. What are the equivalence of the weighting functions? Like this, you have to remember this. So multiply with this weighting function with the given x of n. This is the x of n. 1, minus 1, 2, minus 2. After multiplying this 2, this one and this 2, you will expect that 0, minus 1, minus j, 6, minus j plus j, minus 1 plus j. So therefore, can be defined. It is already determined by using the matrix, find the expected values. That is therefore discrete Fourier transform. DFT is x of n, it is followed by x of k, 0, okay, minus 1, minus j, and 6, minus 1 plus j. Like this, we have to determine if the given sequence or given DFT x of k of the given sequence is x of n is equal to 1, minus 1, 2, minus 2. Okay, next come to this next. So reverse of that. What is that? Just now we are finding that all DFTs, or the reverse of the DFT is IDFT. Find that the IDFT, inverse discrete Fourier transform of x of k, is equal to 4 minus j2 0 plus j2 using discrete Fourier transform. So here the given data, x of k is given 4 minus 2j 0 plus j2. Okay, x of k is equal to 4 comma j2 0 minus j2. Okay, the DFT of the x of k is determined using matrix form. To find the IDFT of the x of k, find the x convolved of x of k, then find the DFT of x convolved of what you call k, then take the conjugative of the DFT x convolved of the k and divide by capital N. Okay, so this just we will try to verify that how it is affected with the DFT and IDFT using this particular example 2.6. Okay, now the DFT, we know that the DFT is x convolved of k, so we know that's all multiplied with this value x of k, 4 minus j2 0 plus what you call j2. Okay, here it is the polarities are changed, minus j2, here it is plus j2. Okay, so here after multiplying this value and this value, okay, now we have to verify that 4, 8, okay, 4, this one is 0. After simplifying this, after multiplying this, after convolving this, that k, x of k. So IDFT, therefore, IDFT, inverse discrete Fourier transform of x of k, is equal to x of n is equal to 1 by 4 of 4, 8, 4 and 0. Simplify this one. After simplifying this, okay, that is 1 by 4 into 4 comma 8 comma 4 0. Okay, that means 4 ones 4 2s, 4 1 0. It is 1 2 1 0. Okay, now come to the next example 2.7. Find the IDFT, inverse discrete Fourier transform of x of k 4204 using the DFT. Here x of k is given, x convol of k equal to 4204. The DFT of the x of k is determined using matrix S below. To find IDFT of the x of k, first find the x convol of k, then find the DFT of xk. Then take the conjugative of the discrete Fourier transform. Then take the conjugative of the DFT divided by n, like this. Right, to verify that IDFT of x of k is equal to x of k is equal to x of n is equal to 1 by 4. Okay, so 1 by 4, that what you call, where we know that DFT, the DFT x convol with k equal to, you know, this all matrix with this value, what value, x of k 4 2 0 4 and so on. After multiplying this using the x convol with a k, okay, after multiplying this 10 4 plus j2 minus 2 4 minus j2, like this, divided by n. Therefore inverse discrete Fourier transform of x of k is equal to x of n is also 1 by 4 of what do you call this finalized value 10, this value, and minus 2 4 minus j2 after simplifying this equation, what do you call, after simplifying this equation, we have to verify that what you call, this is the final answer. This is your IDFT, inverse discrete Fourier transform, for given x of k is equal to 4204 using the DFT. Now next example, find the IDFT, inverse discrete Fourier transform of x of k 1, 0, 1, 0. This is the given sequence. So under this, how we are solving this? The given data is x of k is equal to 1, 0, 1, 0. The inverse discrete Fourier transform of x of k, that is x of n, is determined by using matrix as a form. We know that use the same one, okay, but here it is changed that the DFT of x convol with a k. So this is as usual, and this value is here, and this value is here, x of 0, x of 1, x of 2, x of 3. Okay, so after multiplying this, after convolving this and this, what do you call, so 2, we will expect the 2, 0, 2, 0. Okay, so now therefore the inverse discrete Fourier transform of x of k is equal to x of n is equal to 1 by 4. Discrete Fourier transform of x convol of k, this 1 by 4 2 0 2 2 1 by 4 of 2 comma 0 comma 2 comma 0. After substituting this all values, after simplifying these two values, we will expect the term 0.5 0 0.5 0. This is the simple computing IDFTs. Okay, so sometimes it is reflected by using the different properties. You know that major properties are involved here. Periodicity, what we have discussed, what is reflected because of x of n and n plus n equal to x of n. If a sequence x of n is periodicity with periodicity of n samples, then n point discrete Fourier transform of the sequence x of k is also periodic with the periodicity of capital N samples. Okay, so this is the linearity. We know that all DFT of the even and odd sequence already we have discussed. The time reverse of the sequence. The time reverse of the n point sequence x of n is obtained by wrapping the sequence x of n around the circle in the clockwise direction. It is denoted as x of minus n mod n and what do you call x of that x of minus x of n minus n mod n is also equal to x of n minus n, capital N minus n. That interval 0 less than or equal to n less than or equal to n minus 1. That means where in terms of this x of minus n with what do you call mod n, what do you call with this is also equal to that x of what do you call x of n minus 1 minus n. For using this one interval, that condition 0 less than or equal to n less than or equal to what do you call capital N minus 1. Okay, if DFT x of n is equal to x of k, then DFT of x of minus n mod n is equal to DFT of x of n capital N minus n. Okay, it is also equal to that what do you call x of what do you call minus k, so mod n with this is also equal to that x of capital N minus k. Okay, like this. So right, to verify that all in terms of this verification or proof, DFT of x of n minus n is equal to the summation n is equal to 0 to n minus 1 x of n, okay, and e power minus j 2 pi n k by capital N. Okay, so like this, the time reversal of the sequence is, so it is depending on wrapping the sequence x of n around the circle in the clockwise direction. It is denoted as x of minus n mod n and so on. Change the index from n to m, where m is equal to n minus n. We have n is equal to n minus 1. Now the DFT is ready to verify. So circular frequency shift, if we are using the DFT of x of n is equal to x of k, then DFT of the x of n, the total factor, it is also equal to the x of k minus l and mod n. So right, verify that all proof according to this DFT. With this, go on substituting that all the total factor. It is mentioned the complex consecutive. So sometimes we have to verify the DFT of the delayed sequence, circular time shift of the sequence. Okay, sometimes we have to replace the n by n minus n. We have x of n minus n naught is equal to n naught n is equal to what you call 1 by n, the summation 1 by what you call, it is also equal to that what you call 1 by n, the summation where it is k equal to 0 to n minus 1 x of k, the DFT into the total factor e power j 2 pi by capital N into what you call n minus n naught into k. Okay, so like this on taking the DFT on both sides, we get what you call DFT of x of n minus n naught x into k into e power j 2 pi by n into k. Now DFT of the real value sequence, let x of n be a real sequence by definition of the DFT. The DFT of x of n is equal to x of k. The summation n is equal to 0 to n minus 1 x of n into e power j 2 pi by n into kn. After substituting this, where DFT is equal to what do you call the summation, so the summation of what you call n is equal to 0 to n minus 1 into x of n into cos of 2 pi by capital N into nk. So minus j, the summation n is equal to 0 to n minus 1 into x of n into sine 2 pi by capital N into nk. Okay, like this, where x of k is equal to xr of k plus j into x of k. Therefore, we can see xr of k is equal to this value. Okay, like this, right, to verify. Sometimes we record the multiplication of the two sequences if DFT of x1 of n is equal to x1 of k, and then DFT of x2 of n is equal to x2 of k, then DFT of x1 of n and x2 of n is equal to 1 by n, x1 of k convolved with what you call x2 of it is a circular convolution of x2 of k. Okay, the circular convolution of the two sequences, we are going to represent like this. We know that all the summation k equal to 0 to n minus 1 e power j 2 pi k by n of m minus n minus n is also equal to that the summation k equal to 0 to n minus 1 e power j 2 pi of k into summation what you call 1 power k equal to the summation k equal to 0 to n minus 1 into n. Okay, like this we should follow this all up. Okay, sometimes we require that a linear convolution of the DFT for the efficient computation and so on. The DFT supports only circular convolution. When two numbers of the n-pointed sequences are circularly convolved, it produces another n-point sequences. Because of while we are computing that DFT, discrete Fourier transform, the DFT supports only circular convolution. When two numbers of n-point sequences are circularly convolved, it produces another n-point sequence. For circular convolution, one of the sequence should be periodically extended. Also, the resultant sequence is periodic with the period n. The linear convolution of the two sequences of what you call n1 of n1 and n2. So product of the n1 and n2, the output sequence length is what you call n1 plus n2 minus 1. They perform linear convolution with the DFT. Both the sequence should be converted to n1 plus n2 minus 1 sequence by adding with zeros. Okay, then take the n1 plus n2 minus 1 point DFT of both the sequences and determine the product of the discrete Fourier transform. Yeah, the resultant sequence is given by the IDFT, inverse discrete Fourier transform, the product of discrete Fourier transform. So the time here it is, the response is given by the circular convolution of the what you call the circular convolution of the what you call that n1 plus n2 minus 1. Okay, so here this is the sequence we should follow. Let x of n be the n1 point sequence and h of n be the n2 point sequence. The linear convolution of the x of n and h of n produces a sequence y of n of the length n1 plus n2 minus 1. So adding this, add x of n with n2 of minus 1 zeros and x2 h of n, that h of n with n1 minus 1 zeros. Make both of them of the length n1 plus n1 what do you call n1 plus n2 minus 1. Let x of k be an n1 plus n2 minus 1 point. DFT of the x of n and h of k be and what do you call n1 plus n2 minus 1 point DFT of the h of n. Now the sequence y of n, y of n is given by the inverse discrete Fourier transform product x of k into h of k. So like this, y of n is equal to that output response. Y of n is equals inverse discrete Fourier transform of x of k into h of k. Okay. About technique of technique for convolving that finite duration sequence using DFT sequence is called as fast convolution. The fast convolution. So the fast convolution is it is depending upon what you call it is depending upon, okay, so what it is vary this what do you call this particular case. The case is involved with this, okay, involving this the convolution of the two sequences by convolution of some formula. This technique of the convolving the two finite duration sequence using DFT techniques is called fast convolution. The convolution of the two sequences by convolution of some formula is called direct convolution of the slow convolution. The term fast is used because the DFT can be evaluated rapidly and efficiently using any of the largest class of algorithms called FFT, fast Fourier transform. So in the practice sense, the size of the DFT, discrete Fourier transforms need to be restricted to n1 plus n2 minus 1 point transforms. Okay, so there is the restriction here where n1 plus n2 minus 1 point transforms. Any number L can be used for the transform size subject to the restriction L minus n1 plus n2 minus 1. If L greater than n1 plus n2 minus 1, then y of n will be 0 valued sample at the end of the period. Like this, the technique of the convolving the two finite duration sequence using the DFT technique is you can analyze. Okay, so sometimes we require the convolution technique. The convolution is the slow convolution or fast convolution, but we will evaluate rapidly and efficiently using any of the large class of algorithms called FFT, fast Fourier transform. Okay, you can consider that y of n is equal to summation minus infinity plus infinity x of k into h of n minus k. Like this. So where x of k is equal to summation n equal to 0 to 2 according to your any example that here it is specified the k value. K value is ready to substitute the k value. Before that, we know that a capital N, okay, capital N is decided. Capital N is maybe here it is what you call 3, okay, 3 minus 1, 3 minus that n minus 1 is equal to 3 minus 1 is equal to 2. That's why it is mentioned that n is equal to 0 to n x of n and e power j 2 pi n, where k equal to, here it is gone substituting this all values, k equal to 0, k equal to 1, k equal to 2 and so on. Finally k equal to 0, x of 0 1 plus 2 and e power 0 equal to 3, k equal to 1. So this value is minus j 1.732, k equal to 2, x of k is equal to what you call, so j into 1.732. By the definition of the n-point DFT, 3-point DFT of the h of n is h of k. That h of k is equal to n is equal to 0 to n minus 1 is n equal to 0 to 2 x h of n. That h of n is, by the definition of the n-point DFT, the 3-point DFT of the h of n is h of n and e power j 2 pi by 3 into nk, h of 0 e power 0 plus h of 1 e power minus j 2 pi by n is 3 into k, h of 2 into e power j 4 pi n into k n is after simplifying this 2 plus e power j by 3 into k. So when k equal to 0, h of 0 equal to 2 plus 1 equal to 3. Like this, k equal to 1, k equal to 2, and so on. Finally, we have to verify. So the sequence y of n is obtained from the IDFT of y of k by definition of the IDFT. So this all we know that y of n is equal to like this. If when in this case y of n is equal to 1 by 3, because of IDFT, right, to verify, we are computing that y of n 1 by 3, the summation k equal to 0 to k equal to 0 to 2, y of k into e power j 2 pi by 3 into mk. So 1 by 3, y of 0. So y of 1, that is n is equal to 0, where n is equal to 1, where n is equal to 2. So n is equal to 0 and 1 and 2. So we have to verify that when n is equal to 0, y of 0 equal to, so 1 by 3, y of 0 plus y of 1, y of 2. So all values we know that all. So finally that n is equal to 0, y of 0 equal to 2, y of 1 is equal to 5. After simplifying this, where n is equal to 0 is 2, n is equal to 1, y of 1 is equal to, so 5. So like this, n is equal to 2 and so on. The linear convolution of x of n 1, 2 and h of n is obtained using the tabular method is like this. The tabulation method. Here it is normally. So I have to verify that. Now here where x of n is 1, 2 and here it is 2 and 1. So like this, here it is 2 ones are 2, 1 to 1 and 2 twos are 4, 1 twos are what you call 2, like this. After that, from this table we have to verify that y of n, where y of n is equal to what we call 2 comma 1, 1 plus 4, this 2 value plus comma 2. So therefore y of n is equal to 2 comma 5 comma 2. Since we can consider this, the linear convolution of x of n is 1, 2. It is using the tabulation 2, 5, 2. Like this. Try to verifying this. What do you call? The linear convolution of the sequence is verified. Similar cases, using this simple example, find the linear convolution of the sequences x of n and h of n using the DFT. X of n is given 1, 0, 2. H of n is 1, 1. Now under this, let y of n be the linear convolution of x of n, h of n. X of n is of length is 3, h of n is length of 2. This length is 3, isn't it? Where this length is 2. Okay. So the linear convolution of the x of n and h of n will produce a 4 sample sequence. 3 plus 2 minus 1 is equal to 4. To avoid the time aliasing, we convert the 2 samples and 3 sample sequence into 4 sample sequence by padding with the zeros. Okay. So like this, x of n is equal to, where x of n is equal to 1, 0, 2 here this case. Normally it is given that 1, 0, 2. Okay, after padding with zeros, now 1, 0, 2, 0 after padding. So here h of n is 2. After padding this here, normally we know that h of n is given as 1, 1. After padding 2, padding here 0 and 0. So finally h of n is this one. By the definition of the n quantity DFT, The 4-point DFT of x of n, ready to evaluate, ready to compute, that are defining the linear convolution of the sequence x of n and h of n DFT. Okay, like this you should follow, where x of k is equal to the summation n equal to 0 to 3 x of n e power j minus j 2 pi by n is 4 kn x of 0. Okay, x of 0 e power 0, x of 1 e power minus j pi by 2 into k plus kx into what you call x of 2 into e power j pi k plus x of 3 into e power j 3 pi by 2 into k. Like this, when k equal to 0, and k equal to 0, so 3. When k equal to 1, minus 1. When k equal to 2, 3. K equal to what you call 3, okay, minus 1. Therefore, x of k is equal to 3, 1 minus 1 plus 3 minus 1. Where the definition of the n-point DFT, 4-point DFT of h of n is, okay, is like this. Okay, therefore, y of k is ready to evaluate this value. Okay, so like this we are ready to evaluate this type of problems. Of that we can decide the factors. Okay.
Like, share and subscribe. Hit the bell icon for more updates.